Hello, my name is Patricia Rose de Leon, and today I will be doing the sixth Talk to the Text assignment for the class Introduction to Human Physiology. So, in this assignment, not only will I show you my thought processes, but I'll also show you my annotation processes. So, yeah, this assignment is all about action potentials, and since it is 5 page worth of information, I'll just get started right away. And also, just a quick note before I begin, I will read the text from left to right in that order, just so you guys can follow along and not have any confusion at all. So yeah, 5 page word. Okay, so I'll begin on the left side here, and let's get started. So, Unit 3, Regulation and Integration of the Body. So, Figure A shows depolarization, a small patch of the membrane, a red area right here, and depolarizes. So, it seems like when there's a stimulus put here, it depolarizes plasma membrane. And B, depolarization spreads. Opposite charges attract each other. This creates local currents, black arrows that depolarize adjacent membrane areas, spreading spreading the wave of depolarization. See, membrane potential decays with distance. Because current is lost through leaky plasma membrane, the voltage declines with distance from the stimulus. The voltage is decremental. Consequently, graded potentials aren't short distance signals. So figure 1110, the spread indicate of graded potential. So I'm assuming this is information that is not connected to any other text that is relatively included in this um, portion. But in case that figure 11.10 is needed for other text mentioned here in the PDF, then I might as well look over it later. Since this is cut off, I will ignore this and then move on here instead. So for our patch of plasma membrane, positive ions, mostly potassium ions inside the cell, move away from the depolarized area and accumulate in neighboring membrane areas, where they neutralize negative ions. Meanwhile, positive ions in the outer membrane face move toward the region of reversed membrane polarity, the depolarized region, which is momentarily less positive. As these positive ions move, their places on the membrane became occupied by negative ions, such as chloride and I believe that's bicarbonate, sort of like ionic musical chairs. In this way, at regions abutting the depolarized region, the inside becomes less negative and the outside becomes less positive. In other words, the depolarization spreads as the neighboring membrane patch is in turn depolarized. Okay, before I start analyzing what this paragraph means, I think it's important to kind of give me a short, like, put a short note of terms that I need to remember before analyzing it. So I need to remember that graded potentials are they are short lived. They are short lived and they localize changes in membrane potential, so that it can either be like, depolarizations or hyperpolarizations. So yeah, so can either be depolarizations or Hy- Hyperpolarizations. So yeah, and these changes they can be polarizations. The changes can be they can cause current they can cause current flows that decrease in magnitude with distance, which was something that was mentioned in the earlier text that I've read. These current flows decrease in magnitude with distance. It's too big. I might have to leave some space. Maybe. Okay, so that's something that I need to remember when talking about this paragraph. So, mm, okay. So I think to kind of visualize what happening here, let's say like suppose um like a stimulus depolarizes like a small area of a neuron's plasma membrane. So what happens then? I think it should I think what happens is that the current ions flows on both sides of the membrane between like the depolarized or which called the active membrane area and the kind of like adjacent polarized resting area. And the positive ions they move towards like more negative areas, and the direction of like the cation movement is the direction of like the current flow, and the negative ions they simultaneously move towards more positive areas. So I think that's what they mean by this scenario. I just gave like a small example of what it actually is, but you know so let's say positive ions migrate toward more negative areas, and the direction of the cation movement. Oops, sorry. Cation movement is the direction of the flow. And so basically, like the negative ions, they simultaneously move towards the positive areas. Negative ions move positive areas. Okay, I feel like my texts are too big. I might have to um, make it smaller so there's more spaces for my other annotations for later. Hopefully, it's not too confusing, but if you guys if you need me to change anything with my annotations, I'll gladly change them, um, just so it'll be more easier for you guys to look at it. Okay, so moving on. As just explained, the flow of current adjacent membrane areas changes the membrane potential there as well. However, the plasma membrane is permeable like a leaky water hose, and most of the most of the charge is quickly lost through leakage channels, and consequently, the current dies out within a few millimeters of its origin and is said to be decremental. Okay. So I'm not sure what decremental means. I might have to look it up, but for now, I'm gonna highlight it in red just to kind of signify that I need to, oops, to add a note there for later. And because the current dissipates quickly and decays declines with decreasing distance from the site of the initial depolarization, graded potentials can act as signals only over very short distances. Nonetheless, they are essential in initiating action potentials, the long distance signals. So that is something pretty important to remember. I'm going to highlight it in blue to know because it tells us what specifically graded the role of graded potentials is when determining action potentials. Okay, so yes, I might want to put a note here for myself. Look over the meaning of decremental. Look over the meaning of decremental. And for this highlight, I might want to put um, also, because it was a bit confusing for me at first to recognize the difference between the graded potentials and the action potentials, I will put a short note on this side right here. Action potential and graded potential, just so I'm not as to confuse what's like as what their different is. So from what I remember, action potentials are they are large depolarizations. They, they are large depolarizations that can be like transmitted over like long distances. That can be for large depolarizations for long distances. For graded potential, as mentioned here in the highlight section, they are um, basically they're like variable strengths. They're like variable strength signals um, for short distances. So yeah, I think what that's one of the um, main difference between the action potential and the graded potential. Action potential basically for long distances, graded potential for short distances. So yeah, put that right here. Okay. Okay, so let's move on. Action potentials are AP. The principal way neurons send signals over long distances is by generating and propagating or transmitting action potentials. Only cells with excitable membranes, neurons, and muscle cells can generate action potentials. I think that's a pretty important information that needs to be highlighted, just so we're reminded that only action cells only excitable membranes like neurons and muscle cells can generate action potentials. So, an action potential or AP is a brief reversal of membrane potential with a total amplitude change in voltage of about 100 millivolts, from negative 70 millivolts to positive 30 millivolts. Depolarization is followed by the repolarization and often a short period of hyperpolarization. The whole event is over in a few milliseconds. Unlike graded potentials, action potentials do not decay with distance. Okay, so I will highlight the meaning of action potentials just so we're reminded to know just so we're reminded that I know where I can look for the brief meaning of action potentials. And I remember that I mentioned this in the my annotations before, but I will highlight this as well. Okay, so if I remember the information that I was taught back in my AP psychology class, and I think I should take it down, put it down here as an annotation, is that action potentials, they are they're important because they're important in terms of in function for the brain because they propagate information in the nervous system to the central nervous system, and they also propagate commands that is initiated in the central nervous system to the peripheral nervous system. So yeah, I think I should take that down just so I just also have information from my AP psychology class here in this text that is related to the function of the brain. So action potential, it is important because it helps in the helps propagate information in the nervous system to the central nervous system and propagate commands initiated initiated in the CNS or the central nervous system to the peripheral nervous system. Peripheral nervous system. Okay, so now that we have that in the annotation right here, I guess we can move on to the next. So the events of action potential generation and transmission are identical in skeletal muscles and neurons. As we have noted in the neuron, an AP is also called a nerve impulse. An AP is also called a nerve impulse. Oops. Okay, let's get rid of that. It's a bit hard to annotate with Cami sometimes, but you get used to it. So yeah, and is typically generated only in the axons. A neuron generates a nerve impulse only when adequately stimulated. The stimulus changes the permeability of the neuron's membrane by opening specific voltage-gated channels in the axon. So these channels open and close in response to changes in the membrane potential. Channels open closely and close in response to changes in the membrane potential. They are activated by local currents, also known as graded potentials, that spread toward the axon along with dendritic and cell body membranes. Okay, so basically a nerve impulse is, from how I interpreted it from the text, is that it's used to relay a code signal from a nerve cell to an effector. So in response to a stimulus. And by that I think it's used for communication between nerve cells to the other. So yeah, I'm just gonna put this right here. Okay, so basically a nerve impulse. It is relay a coded signal from a nerve cell to another cell in response to stimulus. And because I do notice that the information can that the annotations that I put can be mistaken for the actual text. I think I should change the color of the annotations just so it won't be confusing. So yeah, I think I will just change this to dark blue. Dark blue. Just so it doesn't get is not confusing to look at when you're reading the text. Okay. This should be a highlighted red because I need to look up the meaning of decremental first. Anything that is highlighted in blue should have a connection. Any text that is highlighted that is colored blue should have a connection with the highlighted text. Okay, so now that I'm done with that, I guess I could move on to the next paragraph. So, in many neurons, the transition from local graded potential to long distance action potential takes place at the axon hillock. Axon hillock. In sensory neurons, the action potential is generated by the peripheral or axonal process just proximal to the receptor region. However, for simplicity, we'll just use the term axon in our discussion. We'll look first at the generation of an action potential and then at its propagation. Okay, it doesn't actually mention the definition of an axon hillock, but if I remember correctly from my previous readings, I should be able to confidently give a meaning of it and then connect it back to the information mentioned in the text. So I'll put it right here. So basically, let's see here. If I remember correctly, um, an axon hillock is something. It basically acts like a manager in a way. It acts like a manager that like sums the total inhibitory and the excitatory signals. Basically, summing the total inhibitory and excitatory signals. Okay, I have to make this a bit more smaller. So yeah, usually if these signals exceed like a certain amount of threshold, basically the action potential will kind of be they'll be like triggered and an electrical signal will be like transmitted down to the axon away from the cell body. So yeah, basically the axon hillock is something that sums the total inhibitory and the excitatory signals. Okay. Moving on, degeneration of an action potential. Focus on an action potential figure 11.11 on page 402 to 403 describes how an action potential is generated. Let's start with a neuron in the resting polarized state. Um okay. So this is the figure 11.11 that it was talking about. I think I should look over um the information provided first before I actually um look over the figure. So number 1, a resting state. All gated uh all gated sodium and potassium channels are closed. Only the leakage channels are open, maintaining a resting membrane potential. Each sodium channel has two gates, a voltage-sensitive activation gate that is closed at rest in response to depolarization by opening, and an inactivation gate that blocks the channel once it is open. Thus, depolarization opens and then inactivates sodium channels. Highlight this, highlight activation gate. Okay. Oh my god. Activation gate and inactivation gate. So basically, from how I interpret it, so basically in this state is that all of the channels are open, but from the resting state to the depolarization state, the depolarizing phase, it would let's try right here. So from one, which is the wait, let me just put two. From the resting state to the depolarization state or the depolarization phase, this will be from closed. Okay, I'm sorry if this is not really neat. I'm using a mouse to write this down, but hopefully it's understandable. So from resting state, the channels are closed, but once it depolarizes, the channels will be open. And so the depolarization um so yeah, basically it says here that depolarization opens and then inactivates the sodium channels. But why is that actually? So depolarization, my laptop is lagging a bit, so um I'm very sorry if it's taking a bit too long for me to type it down. So yeah, depolarization is kind of necessary for in order to open these channels, and then therefore it acts to activate itself. It acts to activate itself in a regen- regenerative cycle. Regenerative cycle. Let me just make this a bit more smaller so there's space for me to add more information. So yeah, what I mean by that is that the sodium influx, like sodium influx depolarizes the membrane, which opens more channels, which polarizes the membrane more. So any influx depolarizes the membrane, which opens more channels, which depolarizes the membrane more. Okay, so let's move on. Both gates must be open in order for sodium to enter, but closing of either gate effectively closes the channel. By contrast, each active potassium channel has a single voltage sensitive gate that is closed in a resting state and opens slowly in response to depolarization. Okay, so for this part, which says that each active potassium channel has a single voltage sensitive gate that is closed in the resting state and opens slowly in response to depolarization. So, I am a bit confused as to what that actually means. So, I will highlight it in red and then put my question here at the top saying how does depolarization, more specifically, what is the process involved? How is depolarization, or what is the process involved that lets that allows the active potassium channel to in open to slowly open in this stage. Okay. So yeah, I'm a bit confused as to what that actually means, but hopefully I can address some of my concerns with it. I'm gonna put a arrow here just to indicate which one I'm confused about. So the second phase is defolarization, and which are the sodium channels open as local which the sodium channels are open. As local currents depolarize the axon membrane, the voltage-gated sodium channels open and sodium rushes into the cell. This influx of positive charge depolarizes the local patch of the membrane, further opening more sodium channels so the cell interior becomes less negative. And when depolarization at the stimulation site reaches a critical level called threshold, often between -55 and -50 millivolts, depolarizations become self-generating, urged on by positive feedback. That is, after being initiated by the stimulus, depolarization is driven by the ionic currents created by the sodium influx. As more sodium enters the membrane depolarizes further and opens still more channels until all sodium channels are open. At this point, sodium permeability is about 100 times greater than in a resting neuron. As a result, the membrane potentials become less and less negative and then overshoots to about positive 20 millivolts as sodium rushes in along its electrochemical gradient. This rapid depolarization and polarity reversal produces the sharp upward spike of the action potential. Okay, before we move on to the second paragraph, I want to highlight some important key information that I've learned in this paragraph. First, okay, let's move on. Before I talk about the information that I learned in this paragraph, I'll finish this text about depolarization phase first. So earlier we stated that the membrane potential depends on membrane permeability, but here we say that membrane permeability depends on membrane potential. Can both statements be true? Yes, because these two relationships establish a positive feedback cycle. An increasing sodium permeability due to increased channel opening that leads to a greater depolarization, which increases sodium permeability, and so on. This explosive positive feedback cycle is responsible for the rising or the depolarizing phase of an action potential. It puts the action in the action potential. So basically, in summary, during this phase, during in the critical level called the threshold, the voltage gated sodium channels in the membrane they open, which allows more sodium ions to rush into the cell. So this influx of sodium ion makes the membrane potential increase very rapidly, and it goes all the way up to about positive 30 millivolts. So yeah, so I put in here a short summary of what I learned in this text. So at this threshold voltage gated sodium sodium channels in the membrane open, which allows which allow many sodium ions which allows many sodium ions to into the cell rush into the cell. So yeah, basically this influx of sodium ions makes the membrane potential increase very rapidly, going all the way up to 30 positive 30 millivolts. This is basically a short summary of the text here. Hopefully it's pretty understandable, but if not, then I might have to make changes to it later. So I assume after the depolarization, then it will probably the sodium channels will probably inactivate. Okay, so one thing that I've learned about one new thing that I learned in this text is about the positive feedback cycle, which I'm not actually aware of the meaning of. So basically, it's is when the increasing sodium permeability is increased due to channel opening that leads to greater depolarization, which increases sodium permeability, and so on. Okay, so basically, from how I interpreted it, is basically the positive feedback cycle is something that develops exponentially, which drives the membrane potential toward the positive values. So let me just put it right here. It is the positive feedback cycle is something that develops exponentially, driving the cell membrane driving the cell membrane potential toward the positive values. I feel like I should use a different annotation tool after this because Cami it is I don't know. Sometimes it can be tricky to use Cami. It can be frustrating sometimes, but I could deal with it anyways. Okay, so let's move on to the next phase, which is the repolarization, which is where the sodium channels inactivate and the potassium channels open. So the explosively rising phase of the action potential persists for only about 1 millisecond. It is self-limiting because the low inactivation gates of the Na channels begins to close at this point. As a result, the membrane permeability to sodium declines to resting levels and the net influx of sodium stops completely. Consequently, the AP spikes stops rising. As sodium entry declines, the slow voltage gated potassium channels open and potassium rushes out of the cell. Following its electrochemical gradient, this restores the internal negativity of the resting neuron, an event called the repolarization. This restore okay. So both of the abrupt decline in the sodium permeability and the increased permeability of potassium, contribute to repolarization. Okay, so from phase 2 to 3, which is depolarization to repolarization, um, see, from D, which is repolarization, to R, which is repolarization, basically the channels become, well, they're open in depolarization, and then they become closed. And oh wait, no, they become open in depolarization, but they become inactive. Inactive in repolarization. And so basically during this phase, um let me just put it right here. Okay, I'm sorry, the camera is lagging a bit. It's lagging a bit behind, but so during this phase, which is basically from open to inactive, depolarization polarization is also necessary to inactivate the channel. What I mean by that, it therefore acts to activate itself in the um no I'm sorry basically in this phase depolarization is also necessary to inactivate the channel. So once the channel is open, it will then also switch to the inactive state and um oh yeah, and then it also switched to the inactive state and it can't be opened again. So inactivate the channel, and once the channel is open, it it will then also switch to the inactive state and cannot be open again. So yeah, basically repolarization is like this stage of the action potential in which like the cell experiences like a decrease of voltage due to like the influx of potassium ions along with like its electrochemical gradient. So yeah, this phase occurs after the cell reaches its highest voltage from depolarization. So here, after the cell reaches its highest voltage in depolarization. Where can I put this? You know what, I think I will just put this here. And then just draw a line here. Okay, moving on to the last phase actually, which is hyperpolarization, which were which is some potassium channels remain open and sodium channels reset. The period of increased potassium permeability typically lasts longer than needed to restore the resting state. As a result of the excessive potassium efflux before the potassium channels close, a hyperpolarization is seen on the AP curve. Let me just pull up my annotation tool. Okay. As a result of the excessive potassium efflux before the potassium channels close, a hyperpolarization is seen on the AP curve as a slight dip following the spike. Also, at this point, the sodium channels begin to reset to their original position by changing shape to reopen their inactivation gates and close their activation gates. Repolarization restores the resting electrical conditions, but it does not restore resting ionic conditions. Oh my god. Okay. Highlight that. That's a pretty important statement. After repolarization, the sodium potassium pump redistributes the ions. While it might appear that tremendous amounts of sodium and potassium ions changes places during an action potential, this is not the case. Only small amounts of sodium and potassium ions cross the membrane. The sodium influx required to reach the threshold produces only a 0.012% change in the intracellular sodium concentration. These small ionic changes are quickly corrected because an axon membrane has thousands of sodium and potassium pumps. Okay, so let's talk about this paragraph first. So from phase, let's just put it here. Okay, so from phase 3 to 4, which is repolarization to hyperpolarization. So repolarization to, okay, that's a bit too long, but repolarization to hyperpolarization, it becomes inactive. Okay, to close. Okay. So from this phase, the channel will actually not switch back to the closed state until the membrane has repolarized. So if it has gone back towards the original resting state, then um yeah, if it gone back towards the original resting membrane potential. But once in the closed state, it can then be reopened. So in this phase, the channel will not go back, will not switch back to the closed state until the membrane has repolarized. Okay. So basically, in this state, so yeah, eventually once the voltage for potassium channels stay open a little longer than needed to like bring the membrane back to its resting potential, eventually the voltage gated potassium channels they close and the membrane potential stabilizes at like the resting potential. So the sodium channels they return to the normal state, like remain closed, but they become responsive to the voltage. So yeah, basically after that the action potential cycle may then repeat after that. So the sodium potassium pump, did I put a highlight on it? Oh, yeah. So basically, sodium potassium pump is something that is kind of like used to transport sodium and potassium ions across the cell membrane. And yeah, so in this process, the pump is usually used to help stabilize membrane potential, and it's kind of like essential in creating the conditions necessary for firing the action potential. So I might as well put that information that I said in here. But before I do, I need to fix. I don't know why, but Cami can be a little slow sometimes. Okay, let's just don't mind that highlight and put the annotation right here. So basically, the sodium potassium pump is used to transport sodium and potassium ions across the cell membrane. And with that being said, it is important because it stabilizes the membrane potential and it's essential for creating the conditions necessary for firing the action potential. After this one, I might probably have to switch to another annotation tool because of how laggy this Cami can be. So, moving on, threshold and the all or none phenomenon. Not all local depolarization events produce APs. The depolarization must reach threshold values of an axon if an axon is to fire. What determines a threshold point? So, yeah, the main question in this paragraph will be what determines the threshold point? So, it says here one explanation is that the threshold is the membrane potential. Oh my god. I did not mean to highlight all of them text. So I think that's what happens when you just scan the text with OCR. it scans pretty much everything. But so one explanation is that the threshold is the membrane potential at which the outward current created by the potassium movement is exactly equal to the inward current created by the sodium movement. Threshold is typically reached when the membrane has been depolarized by 15 to 20 millivolts from the resting value. This depolarization status represents an unstable equilibrium state. If one or more sodium enters, further depolarization occurs, opening more sodium channels and allowing more sodium to enter. If, on the other hand, one more potassium leaves, the membrane potential is driven away from this threshold. Sodium channels close, and then potassium continues to diffuse outward until the potential returns to its resting value. Okay, so in other words, I'm gonna label this number one, this paragraph number one, because I don't have space to actually put in the annotation here. But in other words, that paragraph is that changes in the ion conductances of sodium and potassium ions can lead to either like a raised or lowered value of the threshold. So changes in the ion conductances of sodium or potassium ion can lead to either a raised or lowered value of threshold. Conduct. Didn't I spell it right? Conductances. Okay. Okay, moving on. Recall that local depolarizations are created potentials and their magnitude increased when stimuli become more intense. Brief weak stimuli, subthreshold stimuli reproduce subthreshold depolarizations that are not translated into nerve impulses. On the other hand, stronger threshold stimuli produce depolarizing currents that push the membrane potential toward and beyond the threshold voltage. As a result, sodium permeability rises to such an extent that entering sodium's swamp or exceed the outward movement of potassium, establishing the positive feedback and generating an AP. So this is knowledge that is actually found in the fifth fifth think aloud assignment. It's information that's been already stated in that assignment. So I think I'll just serve this as a review. I won't necessarily annotate anything in it because I believe I already talked about this in my previous assignment, but yeah. So, moving on, the critical factor here is the total amount of current that flows through the membrane during a stimulus or electrical charge times time. Strong stimuli depolarize the membrane to threshold quickly. Weaker stimuli must be applied for longer periods to provide the crucial amount of current flow. Very weak stimuli do not trigger an AP because the local current flows they produce are so slight that they dissipate long before the threshold is reached. Okay, so based from this statement, would that actually mean, let me just put, oh my god. So based on that, oh, okay. Based on that statement, how does the how does the stimuli strength affect the action potential? Would it mean like would it mean if the stronger stimulus equals to like higher frequency at which AP is generated? So that is a question that I'm curious about when reading that statement about the very weak stimuli not causing the um not triggering an AP. So an AP is an all or none phenomenon. It either happens completely or doesn't happen at all. We can compare the generation of an AP to lighting a match under a small dry twig. The changes occur during where the twig is heated are analogous to the change in the membrane permeability that initially allow more sodium to enter the cell. When that part of the twig becomes hot enough, when enough sodium enters the cell, it reaches the flash point threshold and the same consumes the entire twig. Even if you blow out the match, similarly, the AP is generated and propagated whether or not the stimulus continue. But if you blow out the match before the twig reaches the threshold temperature, ignition will not ignition will not take place. Likewise, if the number of sodium ions entering the cell is too low to achieve threshold, no AP would occur. So before I move on to read the rest of this text, I would then proceed to analyze the figures given in this PDF. So figure 11.11, the action potential is a brief change in the membrane potential. I just forgot to highlight this sentence. It is pretty important to remember. So the action potential AP is a brief change in the membrane potential in a, quote, patch of membrane that is depolarized by local currents. The big picture. This graph shows how voltage changes over time at a given point inside an axon during the course of an action potential. So number 1 is probably the resting state, 2 depolarization, 3 repolarization, 4 hyperpolarization. So during the resting state, no ions move through the voltage gated channels. And it's at negative 70 millivolts. And depolarization is caused by the Na flowing into the cell, which, as you can see here, membrane potential increases. Repolarization is caused by the potassium flowing out of the cell. So since potassium is flowing out of the cell, the action potential decreases. So, and number 4, hyperpolarization is caused by the potassium continuing to leave the cell. So I guess from that statement alone, we can assume that um, more um, more K plus or potassium ions means the AP, the action potential decreases. Okay, I got caught off at that part, but basically what I was saying is that, but as there is more potassium ions being released, basically the action potential or the membrane potential decreases. Okay, so this is basically what we talked about earlier in this different phases of action potential. It's pretty self-explanatory, and I think I can understand what this graph means. So the AP is caused by permeability, changes in the plasma membrane. Relative membrane permeability tells you the relative number of ion channels that are open for each ion. Remember that open ion channels make the plasma membrane permeable to those ions. So in Na permeability, which is where sodium channels open, causing depolarization. And sodium permeability, sodium channels open later over a long time interval, causing repolarization and hyperpolarization. Okay, so this is the this basically this graph shows how AP is caused by permeability changes in the plasma membrane, but I'm gonna add a little annotation here as to what those actually mean. So during upstroke during upstroke or during upstroke of action potential, which is going up, the Na permeability or the sodium permeability increases due to opening of sodium channels. Also, just to keep in mind, membrane potential is approaches ENA. However, during a downstroke or going down of action potential, sodium permeability decreases due to inactivation of sodium channels. So one thing to remember here, going upstroke means increasing going up means Na permeability increases, but going down means Na permeability decreases. But during this phase also, the K permeability also increases due to opening of the K plus channels. Also, another key mind to keep in mind is membrane potential approaches EK. However, in number 4, which is the hyperpolarization. So after hyperpolarization of membrane following an action potential. This is not always seen. This is not always seen. Can This is not always seen, but during this phase there is an increased K plus or sodium conductance due to delayed closure of K plus channels. Okay, so I think I pretty much understood what this graph means, but let's move on to this. The key players. So voltage gated sodium channels have two gates and alternate between three different states. So I guess this visual information is all about the sodium and the potassium channels. I don't know if they're gonna talk about the chloride as well, but yeah, this is actually I've actually learned this um, in the I believe it was the reading aloud assignment number 5. So yeah, if I'm gonna put a I'm gonna put an assignment the assignment number here just so I'm reminded as to where I can find additional information about this. So yeah. So yeah, let's just keep reading. So closed at the resting. So number one, outside the cell, inside the cell activation state. So we can see here, it's open. Wait, no, it's actually closed. I didn't realize there was. So yeah, the activation gate is closed. And here, closed at the resting state. So no sodium enters the cell through them. But in the second um phase, it says here, so yeah, as we can see here, the activation gate is open and the sodium ions enter. Open by depolarization, allowing sodium to enter the cell. And as we can see here, the inactivation gate closes the channel, but there's still sodium ions outside. So inactivated channels automatically blocked by inactivation gates soon after they open. Voltage gated potassium channels have one gate and two states. One is that it is closed at a resting state, so no potassium exits the cell through them, and open by depolarization after delay, allowing potassium to exit the cell. So the events. So number one is the resting state. So actually, I guess for the first part um we saw the um graph representation of the steps of action potential, but this one is the visual kind of more representation of it happening. So during the resting state, all gated sodium and potassium channels are closed, but during depolarization, the sodium channels open, and during the repolarization, sodium channels are inactivating and potassium channels open. And during the last phase, which is hyperpolarization, some sodium channels remain open, and some potassium channels remain open and sodium channels reset. So yeah, these are just a repeat of the review that I did of the different steps of action potential earlier. But before I actually move on, I think I want to put a label on these images right here, so I'm not confused as to what they represent. So this is the Na, or the sodium channel, and this is the potassium channel. So this yellow part right here is probably the cytosol. Okay. It's probably the cytosol, and this outside of the cell is probably the extracellular. Just another reminder right here. I'm only using a mouse to write this down, so I'm sorry if this is taking a bit too long. Extracellular fluid. And this right here, the kind of lines is probably the plasma membrane. Okay. So yeah, just wanted to put it out that right there so I'm not confused about the parts. Okay. So moving on to the last page, which is this part. Okay, Okay, I'm gonna read this text first and then look at this figure. So the propagation of an action potential. If it is to serve as the neuron's signaling device, an AP must be propagated along the axon's entire length. As we have seen, the AP is generated by the influx of sodium through a given area of the membrane. This influx establishes a currents that depolarize adjacent membrane areas in the forward direction away from the origin of the nerve impulse, which opens voltage-gated channels and triggers an action potential there. Figure 11.12. Okay, okay, so this is pretty. Okay. So a time 0 millisecond action potential has not yet reached the recording electrode. Time is equals to 2 millisecond action potential peak reaches the recording electrode, and time is equals to 4 millisecond action potential peak has passed the recording electrode membrane at the recording electrode is still hyperpolarized. So I'm actually pretty confused how to analyze and depict the given figure. I might have to look it up, but so yeah, the kind of graphs I'm seeing here is pretty confusing, and I might have to look for explanation for that. Yeah. So I'm gonna highlight this sentence right here. An AP must be propagated along the axon's entire length. So because the area where the AP originated has generated an AP, the sodium channels in that area are inactivated and no new AP is generated there. For this reason, the AP propagates away from its point of origin. If an isolated axon is stimulated by an electrode, the nerve impulse will move away from the point of stimulus in all directions along the membrane. In the body, APs are initiated at one end of the axon and conducted away from that point toward the axon's terminals. Once initiated, an AP is self-propagating and continues along the axon at constant velocity, something like a domino effect. Following depolarization, each segment of axon membrane repolarizes, which restores the resting membrane potential in that region. Because these electrical charges also set up local currents, the repolarization wave chases the depolarization wave down the length of the axon. The propagation process we have just described occurs non-myelinated axons. On page 405, we will describe the propagation along myelinated axons. Although the praise conduction of a nerve impulse is commonly used, nerve impulses are not really conducted in the same way that an insulated wire conducts current. If neurons are fairly poor conductors, as noted earlier, current flows current flows decline with distance because the charges look through the membrane. The expression propagation of the impulse is more accurate because AP what just happened? Okay. Oh my god. This is also more accurate because the AP is regenerated anew each membrane patch, and every subsequent AP is identical that one was generated initially. Okay, so I put a small annotation right here just to kind of add a bit of information that I know of through this process of propagation of an action potential. So the action potential generated at the axon hillock propagates as a wave along the axon. The currents flowing inwards at a point on the axon during an action potential spread out along the axon and depolarize the adjacent sections of its membrane. So coding for stimulus intensity. Once generated, all APs are dependent of stimulus strength, and all of APs are alike. So Can the CNS determine whether a particular stimulus is tense or weak? Information it needs to initiate an approximate response. The answer is really quite simple. Strong stimuli generate nerve impulses more often in given time interval than do with stimuli. Stimulus intensity is coded for by the number of impulses per second. That is by the frequency of action potentials and an increase of the stern amplitude of the individual APs. Refractory periods when a patch of neuron membrane is irradiating an AP and its voltage-gated sodium channels are open. The neuron cannot respond to another stimulus no matter blank. Okay, so a number of things that I learned for the paragraph about coding for stimulus intensity. So number one, the number of receptors activated, population coding, and number two, the frequency of action potentials, frequency coding. So stimulus intensity, as mentioned in this paragraph, is that it is coded by number one, the number of receptors activated, which is population coding, and two, the frequency of action potentials, which is frequency coding. So that is it for the reading aloud assignment number 6, which talks all about the action potentials. I know that this video went over an hour, but I hope that it is enough for me to show my annotation process as well as my thought process when going over this text. So I know that you are watching um, before you guys view the videos, just keep in mind um, that the videos are separated in 3 different parts. The first one is 30 minutes, the second one is 15 minutes, and I believe this one should be around 30 to 40 minutes. But yeah. So because of the because most like online video editors cannot go over an hour, I believe I can edit them and then put them into a singular videos or just separated them into 3 parts. So yeah, I hope you enjoyed watching me do my annotation process and thought process for this assignment, and thank you so much for listening and have a nice day.